presentation is entitled Earth Microbiome Project and its relevance to urban science. And it's going to be presented by Bharath, Prithiviraj, who is a research associate in Earth Environmental Sciences at Prithiviraj.
Good evening all, it's almost 5 p.m. and thanks for staying here. I actually expected to see a common pool of audience, and assuming that, I had a simplified version of the presentation I have here. So without further ado, I'd like to start off acknowledging people who have been involved in mentoring as well as people I work with currently at Brooklyn College, and I have my colleagues here and I work with Peter Grafman. And I want to start off acknowledging my postdoc mentor from my previous term in Boulder, Rob Knight, who was pivotal in co-founding this project that I'm going to be talking to you about. And this is titled the Earth Microbiome Project, and it is a crowdsourced effort of basically assembling microbial diversity information from diverse habitats, basically from different countries all around the globe. And again, those names out there and people who I've worked with, I just want to start off thanking them, as well as Tatiana and George, who've done a tremendous job putting this symposium together. And let's move forward with that. So this was a biogeographic session, and as a school kid, I grew up fascinated about the field of geography. And one of the most striking stories that I heard were these expeditions that explorers like Columbus and Magellan took. And one of the ones that struck me was that of Columbus, and him having to travel up to the Caribbean and thinking that was mainland India, where I originally come from, was a little bit of a fascinating aspect. It was as if that he just believed in that world that exists, and there is no other form of representative landmarks that he could think of in that terms. But of late, I can reflect on this, because right now we are in that space when you talk about ecosystems, when you talk about miniature ecosystems, when you talk about how ecosystems such as soils that are so complex can be even more finer in terms of their resolution. And I think we had that great snapshot on the tree that Darwin put out, and essentially that's one of the most staggering works of research that's compiled together, and for generations to come we are following that in lines of evolution. And again the discovery of the microscope by Anton von Leeuwenhoek was also a revolution, where we were able to appreciate this miniature form of life, and also know that the tree of life essentially is a structure which is a ladder, and it's basically not a ladder, and it's a radiation. And I quote Norman Pace here from the University of Colorado Boulder, who is one of those modern time microbial ecologists who was instrumental in this field surging forward and looking at microbial communities and associations of microbial communities in diverse ecosystems. Is work that he had initiated along with Carl Voss at University of Illinois. And basically, it's at this stage where we have come down to looking at a snapshot of a particular gene that's been conserved extensively in these microbial entities, pretty much bacteria, archaea, and eukaryotes. Or in this case, we're looking at 16S ribosomal RNA, which is the conserved gene that we're examining in bacteria and archaea. And that is one of the most sought-after screening tools that researchers around the world are looking at to enumerate and catalog microbes that you can find in any kind of ecosystem. So with the advances that you're seeing in the field of sequencing of late, in the last 6 to 8 years, you are having an enormous splurge in terms of data that's coming out. And the tree of life that I just showed you earlier is now pretty much getting reformed, because there's so much of sequencing available, and you're able to amplify segments of the genome that can throw light on what kinds of microbes that you would otherwise not be able to culture or grow in a lab, you can examine through these techniques. And this paper came out from the University of California, Berkeley, and it was tremendous to see that you have these superphyla that were originally represented in archaea, which archaeal groups are actually recently discovered groups, and it turns out that the eukaryotes are basically interspersed within that clade. And that itself is mind-boggling in terms of technology and how data put together is advancing the field. So I want to reflect on, again, you would have seen screenshots of such images, again, magnifying what soil is all about. You have this breakup where you're able to examine this structural hierarchy. Here you have sand, silt, and clay that are the physical representatives. Besides that, you have organic matter, plant debris that you can find in soil, and fungi, exopolysaccharides that are released from microbes, and basically colonies of bacteria as well as the protozoans, which would be the associative organisms that co-occur with them. And coming to think of it, we live in a microbial world, and it's come to light from the Human Microbiome project, which came out in 2012. That you are discovering these microbes that coexist on you, as on your surface, and from inside of you, which makes your body as a whole as an ecosystem. So we're seeing that unravel in front of our eyes, and recently you're seeing data that's coming out where they are identifying new microbial communities within the human body, and their roles are very interesting in terms of what health benefits they provide. So we can, synonymous to that, kind of come to a understanding where you can establish analogy between the gut as well as the soils in terms of what they mean to the plants, and these associated microbes could play a pivotal role to improving the soil health and the characteristics of soil health per se. And so one of the important questions that you have in terms of structurally dissecting out what you have in these communities is to examine who is there, and to do that you need to do a taxonomy profiling of who is there, as well as functionally what these entities are doing in their habitats. And so this paper just got published a couple of weeks ago and came out on 23rd of November actually, and it's staggering the number of studies that got assimilated together. 97 studies, 27,700 samples, 2.2 billion sequences in terms of readouts, and 500 researchers as well as contributing to one paper. And this work started off in 2010, and it's been like accumulated work and meta-analysis that are coming out with that work. This is supposed to go all anyway. So these are some of the news clippings of what people were representing from the study, and I'm just going to show you a snapshot of the website that is associated with the study. So essentially, this is mapping the microbiome of everything, which is what the researchers are attempting to do. And it started off as a projection between Rob Knight, Jack Gilbert, and Jan Jansen. He's now at UC San Diego and Argonne Labs, as well as the Pacific Northwest Labs. And it's currently the largest cohort of public access environmental microbiome databases. And this is including at the phase 150 institutions and 264 collaborators. So this is the manuscript that came out. It's openly available. It's an open access Nature article. And a snapshot of some of the sites that have been sampled from. In this case, I'm just going down to the soils because that's of interest here. And if you can particularly see, these are the soil sites that have been sampled, and these are from diverse environments, including you have saline as well as non-saline soil that have been sampled from. So totally accumulating around 6,000 samples for soils in the non-saline as well as the sediment state. This is a website. As you can go up there and look at these characteristics which have been used for delineating habitats specifically. And this is an ontology scale representation where you have host associated information like whether they're free living, whether they're saline, non-saline, and very specific habitat names. And some of the examples include sediments from lakes, ponds, and rivers, soils from forest, grasslands, tundra, and desert, and all these other sample types, including pollen, sap, and tissue of mushroom or other fungi or bark film of mushrooms. These are very diverse sample sets that you have. So I'd encourage you to go and check it out, and you have these snapshot images where you can have trading cards that give you information on what dominant bacteria that you would find, what dominant kind of microbe you would find in a specific habitat, in this case the soil, in terms of the family representation and different habitats there. So I'll skip through that due to lack of time. This is a snapshot of the sequence abundance and the difference between free-living and host-associated sequences in terms of their microbial representation. This is only bacteria and archaea, and you can see in terms of soils, they are again very highly diverse in terms of representation. And in the host-associated, we find the plant rhizosphere. Again, you have the associated microbe effect then with the plants. So I'm going to skip through this due to lack of time here, but you have visualizations where you're able to look at association between different biogeographic zones. You can compare soils that you find in Australia, in Western Australia desert, and just compare it to what you would find in the southwestern desert in the United States. So things like that, you can have visualizations, and do feel free to reach out to folks associated with the project. And I thought that this would be a good framework for leveraging efforts that people are working on. For instance, you have an excellent citizen science-based led screening tool at Columbia, and that would be a very interesting set of metadata that you're collecting, and that can also add to information that these guys are putting together in phase 2. And there are a lot of potentials out there. So even SWEETMA can bring forward a microbiome focus group in their subsequent meetings, where people start talking about the black box, if you will, because it's known that people don't talk about the microbiome because of the costs associated with it, but now with the technology, you're able to bring down costs, and it's possible that you can collaborate with different diverse groups across countries and get work done, as well as have fascinating results coming through. Thank you, and